protection schemes, and indeed the detection of fault conditions, depend very much upon the characteristics of the fault itself. Certainly, the nature of the fault is the principal factor in determining 1. Magnitude of fault current, 2. Change in magnitude of voltages, and 3. Change in phase angle relationships. In this videotape, we shall be looking at the different types of faults and their effects. In this simple one-line diagram, we have a generator feeding power through its circuit breaker and transmission line. The load is 300 amps at a phase to neutral voltage of 21 kV. For simplicity, let us draw this out as a single-phase circuit. This 1.5 ohm impedance here represents that of the generator, while the 0.75 ohms here represents the impedance of the transmission line. As this is single phase, we can calculate the impedance of the load simply by dividing 21 kV by 300 amps. And this comes to 70 ohms. Observe that the load impedance is far greater than the generator and line impedance. The return line also has the impedance of 0.75 ohms, and the current, 300 amps, circulates continuously in this closed single-phase circuit. Now let's see what happens when we add further load. Let's say this is also of 70 ohms, and of course it will be in parallel. Our total load now is 600 amps. Note that when we added load, we effectively reduced the load impedance. In this case, the equivalent impedance of these two loads is equal to 35 ohms. As extra load is added, the voltage at the generator must be increased slightly in order to maintain 21 kV at the load. Let's work out the voltage drop between the load and the source. This is simple. Total impedance comes to 3 ohms. Multiplying this by 600 amps gives us a voltage drop of 1800 volts, that is 1.8 kV. So the internal voltage at the generator is 22.8 kV. Now let's see what happens if we have a direct short circuit at the far end of the line right across the load. The load impedance now falls to 0. As a result, the total current circulating through this circuit will now be 22.8 kV divided by 3 ohms, which equals 7,600 amps. This is a tremendous change in magnitude of current, increasing from 600 to 7,600 amps. And what about the voltage throughout the system? Well, as we consider the short circuit to contain no impedance at all, the voltage across the load will now be 0. And at this point, at the beginning of the line, voltage will be 22.8 kV, the internal generator voltage, minus the voltage drop across the generator impedance. That is 22.8 kV minus 7,600 amps times 1.5 ohms equals 11.4 kV. We know in practice that it is all a lot more complicated than this. We have 3 phases to worry about, and moreover, the impedances may be at different angles and therefore would have to be added vectorially. But the conclusions are very clear. First, note that an increase in load decreases the load impedance and therefore decreases the total circuit impedance. Secondly, as a result of the short circuit, the total impedance is greatly reduced, and the consequent increase in current circulating in the system is dramatic. In our example, it has increased by approximately 13 times. Thirdly, the voltage at the short circuit has decreased to 0, or at least to a very low value. As a result, the voltage all along the line is also reduced. When studying fault conditions, we always consider that the internal voltage of the generator remains constant. This is based on the assumption that the time interval will be extremely short before protection equipment clears the fault. In practice, it is probable that the generator automatic controls may attempt to increase generator internal voltage in order to compensate for some of the voltage drop downstream. However, this would take some seconds and therefore should not interfere with the operation of protection relays, nor with our studies of fault characteristics. Let's take our study a step further now and consider the magnitude and phase angle of the various impedances. Here is another single line diagram, but this time of a more complicated system. The impedances line to neutral are represented here. The generator, the step-up transformer, the transmission line, the step-down power transformer, and here the total distribution circuit, including the distribution transformer, and eventually the impedance of the load. Now, let us plot on a resistance-reactance diagram impedance as seen by a relay located after the generator step-up transformer. First, we have here the impedance of the generator. This is quite a low value and also consists mainly of reactance, as can be seen from the large phase angle. Similarly, the step-up transformer impedance is composed almost entirely of reactance and is therefore close to 90 degrees. The impedance of the transmission line is plotted here at about 60 degrees. The impedance of the step-down transformer is shown at almost 90 degrees. And here is the combined impedance of the distribution line and distribution transformer. Note that the impedance of the distribution system is at a lower phase angle at about 40 degrees. And here we add the impedance of the load, which is of much higher magnitude and also at a much lower phase angle. The power factor of the load is generally in the order of 0.9 to 0.95. The corresponding angle to a cosine of 0.9 is about 25 degrees. The total impedance of the circuit is shown by this line. If we have a short circuit close to the load, you can see that there will be a dramatic decrease in impedance, but its phase angle will increase considerably. As the fault becomes closer to the source, the impedance is much less. Consequently, the fault current will be much higher. It is important to remember that the generator itself contains impedance. This serves to limit the magnitude of fault current, even for a short circuit on the generator terminals. Of course, the short must be cleared quickly to avoid serious damage. Now, these examples that we have been looking at are very simplistic because we are not considering the three-phase system. Here we show a similar simple power system, but this time all three phases are included. The generator is Y-connected and its neutral is grounded. If the load is balanced, the Phasor diagram will look like this. I'm sure you'll remember this from earlier study of electrical fundamentals. The voltages and currents are of equal magnitude and phase displacement. However, a fault occurring on this system will cause considerable imbalance. Let's consider just what types of faults can occur. The most common are three-phase to ground, phase to phase to ground, single phase to ground. With the three-phase fault, all three phases, A, B, and C, will be effectively connected together at the fault location, and a very heavy current will flow through the conductors, but the system will still be balanced. Where all three phases are grounded by a fault, this is considered to be the same as a short circuit across all three phases. The voltage at the fault is reduced close to zero on all three phases, and it remains balanced. The second type of fault is the phase-to-phase, where there is a short circuit between two conductors only. In this case, if, say, phases B and C are connected together, then heavy fault current circulates in phases B and C only. Phase A can continue to provide its load. Another type of fault is the phase-to-phase to ground. Fault current flows in the shorted phases and also to ground. 95% of faults on the power system are single phase to ground. Here, the load will continue to be supplied by all three phases, but there will be a heavy flow of current to ground from the faulted phase. This will circulate back and return up the solidly grounded neutral to the generator. Now, before we go on to study the effects of these faults in more detail, let's take a break. Please switch off the tape now and go through this material in your workbook. In the previous segment, we noted that the neutral of the power source was solidly grounded. This is necessary in order to provide a path for ground fault currents to flow. And it is this flow of fault current that enables relays to detect the existence of the ground fault. Actually, not all systems are solidly grounded. We shall be discussing this in a moment, but first, let's look a little closer at common utility practice in grounding. What is the nature of this ground? Well, all power system installations, such as power stations and substations, are built on ground grids. The grid consists of metal rods driven into the ground at various intervals, and this in turn is connected to a metallic mesh mat. As a result, all of this area is at the same ground potential. The main reason for this is safety. The external metallic frame of switchgear, transformers, substation structure, motors, relay panels, and so on are all solidly connected to the ground mat. You are well aware from your trips to substations that the grounding straps are always of considerable current carrying capacity to provide an easy path for flow of stray currents or fault currents to ground. The potential of all framework throughout the area is at the same ground potential, so providing safety for personnel working in and around the equipment. Even secondary wiring, for example, CTs and VTs, should be grounded to discharge any electrostatic potential. However, it is very important to remember that these circuits should be grounded at one point only. For example, suppose a CT secondary circuit has a ground applied in the switch yard and another at the relay panel. In this situation, the secondary wiring provides a path in parallel with the ground mat. Now, if a ground fault occurs, heavy fault current could flow through the secondary wiring, thereby causing damage to the secondary wiring and also probable misoperation of relaying equipment. Where grounding of the power system is required, it's achieved by connecting the neutral of the source voltage to the ground mat. In this simple arrangement, we see the generator, which is Y connected, feeding directly into a 15 kV line. The neutral point of the generator is connected solidly to the ground mat at the power station. Now, if a single phase ground fault occurs on one of the lines, say due to a defective insulator, the fault current will run down the tower structure into the ground and return through the ground to the ground mat of the power station. From here, the fault current will flow back into the generator neutral, so providing a complete path for circulation. A CT is usually connected in the generator neutral with the secondary, feeding a time over current relay. This ground relay, 51G, will need to be coordinated with other protection devices on the generator and the line. Now, let's look at the more common case where we have a delta Y step-up transformer close to the generator. With the Y side ungrounded and a fault on the secondary, there is no path in the transformer high voltage winding for ground fault current to flow. Therefore, the fault would have no effect on generator or transmission line currents. With the Y side grounded, ground fault current would flow in the faulted phase of the Y winding and would be transformed into the delta winding as shown. Note that the phase to ground fault on the Y side manifests itself as a phase-to-phase fault from the delta side. Thus, generator phase A and phase B relays could detect the fault, as could an overcurrent relay in the neutral of the transformer. An overcurrent relay in the neutral of the generator would protect against ground faults on the delta side of the transformer. Note that if the level of fault current is too low, this relay may not operate at all. But often another path is provided. For example, with high voltage transmission lines, the steel towers are connected together at the top by a bare ground wire or sky wire. This ground wire goes right back to the substation structure, which is, of course, grounded to the mat. Consequently, the ground wire provides a parallel path to current flow through the earth. Similarly, on four-wire distribution systems, the neutral fourth wire is usually grounded. And this, of course, provides an excellent path for ground fault current flow. I'm sure you may already be thinking, but where is the path for ground fault current to flow when the transformer secondary is delta connected? There is no neutral point for grounding. Well, in this case, a neutral point must be provided, and it is quite usual to connect a grounding transformer as shown here. The transformer works on a 1-to-1 ratio with the primary and secondaries connected together in a zigzag arrangement. Here we see the circuit diagram for this connection. You can see that the A primary winding is connected in series with B secondary and so on. This allows only ground fault current to pass through. We have pointed out that in utility practice, the equipment is usually solidly grounded at voltages above 40 kV. Now, at lower voltages, sometimes equipment is grounded through an impedance to limit fault current. An example is the generator neutral. The impedance may be in the form of a resistance or reactor, or perhaps a grounding transformer. The main objective of this is to limit the available fault current. This method is used on systems up to about 30 kV and where the protected area is quite small. For example, in the case of the generator, we are protecting against a ground fault within the generator itself or the short length of line, cable, or bus to the transformer. To give you an idea of the order of magnitude, the grounding impedance may be sized to limit the magnitude of ground fault current to, say, 20 amps. This is far less than would be the case with a solidly grounded neutral, where the fault current could be in the order of, say, 4,000 amps. But what is the advantage of impedance grounding? Well, by reducing the magnitude of fault current, we are reducing the amount of damage that it can do. For example, suppose the ground fault is in the generator winding itself. The very high fault current and resultant arc jumping from the winding to the stator laminations would probably burn and seriously damage the generator. We'll be discussing specific examples of impedance grounding in future tapes, but one point is very clear. When working on the power system, you must be alert for these various methods of grounding. always check the schematic diagrams. The value of grounding resistance or impedance is usually indicated. There is yet one other system that we must mention, and this is where there is no grounding at all applied. Take the case of this three-phase distribution line being fed from an ungrounded Y-connected secondary. The line voltage is 23 kV, that is 13.3 kV line to neutral. So the insulators and the spacing of the conductors will be designed for, say, 15 kV. Now, suppose a solid ground fault occurs on line A, reducing this line voltage to ground potential. The potential of the neutral will rise to 13.3 kV, and the line to ground voltage on lines B and C increases to 23 kV. This will greatly stress and possibly damage the line and equipment insulation.
In fact, where ungrounded systems are used, it is normal to increase the level of insulation to withstand at least line-to-line voltage.
But why would anybody want to run their system ungrounded? Well, one reason could be to ensure continuity of supply. For example, an industrial installation which must have minimum outage. In this case, if a ground does occur on one part of the system, no tripping will occur and power supply will continue. The three phases will continue to feed the load and retain the normal phase relationships. However, this method presents several possible hazards. First, at the fault location, we have a live conductor coming into contact with ground, which may be accessible to personnel. Moreover, there may be an arc present, which, if not interrupted, will cause serious damage by burning. Another problem becomes evident if a second ground occurs at another point in the system, say on another phase. In this case, we have effectively a short circuit between the two phases, and this could cause a serious upset to the system. For all of these reasons that we have just explained, ungrounded systems are rarely used. However, there are sometimes areas of a distribution system operating at, say, 13.8 kV connected in delta, and therefore have no accessible neutral point. In this case, ground detection equipment is usually installed as shown here. This is, in essence, a Y-delta transformer. The Y-connected primary provides a neutral for the delta system, and this is solidly grounded. The delta secondaries of the transformer are connected in series. This is called a broken delta. One side is grounded like this, and the other feeds a ground over voltage relay. If no fault exists, there is negligible voltage across the relay because the balanced voltages produced in the secondaries cancel each other out.
Now, in the case of a ground fault on one of the lines, the voltage to ground on that phase is reduced. This reduces the voltage across the primary of that phase. This will cause a reduction of voltage in the associated secondary. Hence, a residual voltage will appear across the ground over voltage relay to cause operation.
Additionally, indicating lamps can be placed across each secondary, thereby giving indication of which particular phase is grounded. Now, at this point, let's briefly summarize the methods of grounding which you will encounter.
Solid grounding. This is the case with most utility systems above 40 kV. Generators may be grounded through an impedance so as to limit the magnitude of fault current. Non-grounded systems are sometimes used in industry or a continuous power supply is required. Distribution systems are sometimes not grounded, and in this case, ground fault detection equipment must be installed. Delta systems can be grounded with grounding transformers. Safety grounding is essential. All equipment in power stations, substations, switch yards, and so on must be solidly connected to the ground mat.
Now at this point, let's take a break. Please switch off the videotape and thoroughly review this material in your workbook. Earlier, we examined the different types of fault that can occur on the power system.
Any one of these faults could happen in equipment such as transformers or generators or even circuit breakers. But more often than not, faults take place on transmission and distribution lines as they are more exposed.
Now let's take a closer look at the effect of these different types of faults. To do this, we'll need to study the associated phasor diagrams.
Here we see the simple three-phase system functioning under normal, balanced conditions. The circuit has been simplified by removing transformers and breakers. The neutral is solidly grounded in order to anchor the system voltage. This phasor diagram shows the phase relationships and magnitude of the line-to-neutral voltages. Line-to-line voltages are also shown. Note that the voltage between lines A and B leads the phase voltage VAN by 30 degrees, and similarly with the other phases. This we already learned in a previous tape. Now, let's see what happens if a short circuit occurs across all three phases at the end of the line. Referring to the phasor diagram, we see conditions at the fault location. In studying these fault characteristics, it is usual to consider that there is zero load current on the system, so only fault currents are indicated. This set of phasors also represents a three-phase to ground fault. The line voltages are drastically reduced, but they still maintain the same phase relationship. The system is still balanced. The magnitude of line current increases greatly, and it is lagging by approximately 60 degrees on its respective phase voltage. Why is this? Well, this angle is determined by the nature of the system impedance to the fault. That is, the generator impedance and the line impedance. The line impedance predominates, and for a 115 kV transmission line, this is usually about 60 degrees. High voltage lines, 230 kV and up, may have impedance angles as high as 85 degrees. Conversely, low voltage distribution lines usually have a line impedance angle of about 50 degrees.
Well, now let's move on to look at the conditions for a phase-to-phase fault.
In this case, the short circuit is between line B and line C. If you could place a voltmeter between lines B and C, you would find the voltage to be much lower than normal. Similarly, the voltage between line B and ground would be lower, as is line C to ground voltage. The phasor diagram shows this. The short circuit drastically reduces the difference in voltage between lines B and C, that is, VBC. This reduces phase voltages VBN and VCN, and the angle between them to less than 120 degrees. This causes a change in the phase relationship of VAB, which is the voltage between the lines A and B. As we know, this is the difference between VAN and VBN. Subtracting these phasors, we find that VAB moves back in phase angle. It now leads VAN by less than 30 degrees. The magnitude of VAB is also reduced slightly. We can see that this phase-to-phase fault has seriously distorted our previously balanced condition. Now, let's look at the line currents.
As we are considering zero load, IA is 0. The current traveling through line B is feeding the fault, and this will lag by approximately 60 degrees on voltage BC. Once IB passes through the short circuit, it returns along line C. So current IC can be shown at the same magnitude, but 180 degrees apart from IB. Incidentally, there is an easier way to construct this phasor diagram, first by indicating only the phase voltages line to neutral. Here we have VAN, VBN, and VCN. Both VBN and VCN have been depressed in magnitude and phase angle due to the short circuit between line B and line C. We can show the voltage between line B and C like this. Similarly, VAB is the voltage between VAN and VBN, and in the same manner we can construct VCA as the voltage between VCN and VAN. The currents go here. IB is at an angle of 60 degrees to VBC, with IC the reverse of IB. Yet another common fault is the two-phase to ground. This example shows a fault between lines B and C, which in turn is faulted to ground. We have currents IB and IC flowing to the fault, and IG, the ground current, leaving. Thus, IB plus IC equals IG. The resultant phasor diagram is similar to that for the phase-to-phase fault, except the depressed voltages VBN and VCN remain at their pre-fault phase angles. The current in line B and line C lags by a large angle, and this is complicated by the fact that some fault current is flowing to ground. Now here we see the conditions at the fault location for a ground fault on line A. The voltage between lines B and C remains normal, as do also the line B to ground and line C to ground. This is not so for line A to B and line C to A. In both cases, the voltage is reduced due to the fault on phase A. The voltage between line A and ground is drastically reduced. It could fall to 0 if the fault impedance is 0, but usually ground faults do contain some resistance, and therefore a small voltage will remain. The ground current will be high, as it is limited only by the impedance of the line and the return path to the grounded neutral. The flow of fault current through the ground path will actually cause a volt drop and a consequent rise in potential of the neutral at the source. This potential shift may be quite small, depending upon the actual grounding arrangements. As before, we are considering in this example that the load current is 0. Therefore, currents IB and IC would be 0, and they are not shown. At this point, let's quickly summarize the types of faults that we have discussed and their main effects. First, let's look at the three-phase fault and three-phase to ground. At the fault location, the voltage will fall close to 0, and very heavy fault current will flow in all three phases. As in all cases, the magnitude of current is limited by the total impedance of the circuit, plus the impedance of the fault. In the phase-to-phase fault, the magnitude of the voltage between the two shorted phases at the fault will fall close to 0, and a heavy fault current will circulate in those two lines. In the phase to ground fault, the voltage will fall in the two faulted lines, and a heavy current will circulate in these two lines and also to ground. With a single phase to ground fault, the voltage of the faulted line to ground will fall close to zero at the fault location, and heavy fault current will circulate through this line and return through the earth to the grounded neutral. The resistance of the fault itself plays an important part in determining the value of fault current. Indeed, if this is very high, there may be insufficient fault current flowing to operate the relays. All of the faults that we've been studying so far involve short circuits. There are other abnormal conditions arising from open circuits, but these are far less common. Let's look at a typical example of one phase which is open-circuited. And this case will serve to introduce the term ferroresonance. You'll remember from your study of electrical fundamentals that the term resonance refers to the combination of inductance and capacitance that can give rise to extremely high voltage levels. For example, look at this simple series circuit. We have an inductive reactance of 2400 ohms in series with a capacitive reactance of 1600 ohms. The voltage across the circuit is 8 kV. The resistance of this particular circuit is negligible. Therefore, the total impedance of the circuit is 2400 minus 1600 equals 800 ohms. Remember that capacitance and inductance have opposing effects. So the value of current through the circuit is equal to 8,000 volts divided by 800 ohms equals 10 amps. But what is the voltage drop across the inductance only? Well, here we have 10 amps times 2,400 ohms equals 24,000 volts. Similarly, we have minus 16,000 volts across the capacitance. So although only 8 kV is applied across the total circuit, we have very high voltages in individual parts of the circuit. And this is precisely what happens when we have ferroresonance in the power system. Typically, this can occur where we have a delta-connected primary of a distribution transformer. In this system, the distribution line is being fed from a Y-connected secondary with the neutral grounded. As this is a distribution line, fuses are often used, so let's consider the situation where one fuse only blows such that we have one phase open-circuited. This situation can also occur where the lineman opens feeder switches one phase at a time. In the interim period, the transformer is still connected to the other two phases, and currents will circulate in this manner. The return path to ground is through the capacitance of the open line. So now look carefully. We have inductive reactance in the transformer windings in series with capacitive reactance between line to ground. Depending upon the specific values of capacitance and inductance, a very high voltage could arise across the transformer winding and also from the line to ground. This could damage insulators and the winding of the transformer itself. This condition is more likely to occur where voltages are 12 kV and higher, and also where the line capacitance is high, for example, with long lines or where cables are used. When you think of all of the variables in the circuits, this subject of ferroresonance is obviously highly complex, but it is essential that we understand the principle, because we shall be meeting this term in future tapes when we discuss specific installations. Clearly, in designing the power system, the engineer tries to ensure that specific values of impedance and capacitance will not lead to resonant conditions. Incidentally, you may have already perceived that one way of reducing the resonance effect would be to insert a resistance in the neutral of the source transformer. But didn't we already point out that we prefer to have this neutral solidly grounded? This is yet another example of opposing interest and compromise that we often meet in power system design. Well, at this point, we all deserve a well-earned break. It is essential that you become familiar with the concepts presented in this tape to assist in understanding the specific protection schemes that are discussed in later tapes. Please switch off the tape now and take time to thoroughly review this material in your workbook and then go through the questions. In the last segment, we used phasor diagrams to show how conditions at a fault location become distorted from the normally balanced voltages and currents.
The phasor diagram is really a geometric or mathematical representation. We're now going to use another mathematical representation and break the phasor diagram into symmetrical components. This allows us to go a stage further in our analysis of fault conditions. As we already know, under normal operation, the power system is balanced, and there is a symmetrical relationship between the three-phase voltages and currents. Even with a three-phase fault, phase quantities remain 120 degrees apart. This symmetrical relationship helps simplify the calculation of currents and voltages under these conditions. However, when the system is unbalanced, analysis is more complicated. We need to divide the voltages and currents into balanced sets of symmetrical components. Let's look at this a little closer. To begin with, we already know that a generator produces three equal voltages, which are equidistantly spaced 120 degrees apart. We have also already pointed out that the phasor rotation is conventionally counterclockwise, and the normal phase sequence is A, B, C. This means that for any fixed point in space, we would see voltage A, then B, then C, then A, and so on in that sequence. When studying symmetrical components, phase voltages are always used, that is, line to neutral or line to ground. We indicate the positive sequence voltages on our diagram by using the subscript 1. For example, VA1, VB1, and VC1. With a balanced load, the current phasors produced by the generator are also similarly balanced. They'll look like this. Once again marked IA1, IB1, and IC1. For study of balanced faults, such as a three-phase short circuit or three-phase to ground, only these positive sequence components are needed.
But what about unbalanced faults, such as a phase-to-phase fault or a phase-to-ground fault? Well, as we'll see, other components are needed in order to analyze these unbalanced system conditions.
Let's look at the phase-to-phase fault where no ground is present. The fault is between line A and line B. This voltage phasor diagram shows the conditions at the fault. The phase voltage on line C, that is VC, remains at its normal angular displacement, but A and B have been brought closer together by the low impedance of the fault. Now remember, the generator, as always, is still producing positive sequence phase voltages. But at the fault, the voltage phasors look like this, with the different phase voltages being identified by VA, VB, and VC. The voltage at the fault on the unfaulted phase is approximately equal to its pre-fault value, and with our phase-to-phase fault, the positive sequence fault voltages are about 50% of this. How do we get from here to here? Well, obviously, other voltages are present at the fault and are being imposed upon the positive sequence voltages. That is, other voltage phasors must be added to the positive sequence phasors to get fault phasors. We can find the missing components by carefully studying the phasor diagram and adding appropriate phasors. Now, to transpose positive sequence fault voltage VA1 to VA at the fault, a phasor must be added in this direction. Let's call this VA2. Similarly, to transpose VB1 to VB, another voltage, VB2, is at play. And observing carefully, we see that the voltage VC is actually greater than VC1. Another voltage phasor, then, VC2, has to be added to produce VC at the fault location. Now, if we bring all of the transposition voltage components together, we find that they are equidistantly spaced at 120 degrees apart and are of the same magnitude. But look carefully. Considering conventional counterclockwise phasor rotation, the phase sequence is reversed. From our point in space, we will now see phase A, then C, then B, then A, and so on. Just the opposite to the positive sequence, which is A, B, C. So this is known as negative sequence, and the values are normally given the subscript 2. This brings us to a very important conclusion. Where unbalanced conditions exist, negative sequence voltage and current are produced by the fault, and these are superimposed upon the positive sequence quantities. Now let's move along and look at unbalanced faults involving ground. Here we see a phase to ground fault on phase A, and this is the resultant voltage phasor diagram showing conditions at the fault. The voltage on phase A becomes very small, depending upon the impedance of the fault. For simplicity, let's assume this to be 0. The phase voltages on lines B and C remain unchanged. The current in line A, that is IA, increases considerably to feed the fault. Note that we have drawn the current IA in phase with voltage VA. For simplicity, when using symmetrical components, the fault path is considered to be either pure resistance or pure inductance. Throughout this segment, we're assuming the fault path to consist of resistance only, and the current is therefore in phase with the voltage. The current in lines B and C is 0 in both cases, as system load is considered to be 0. Our phasor diagram shows that the system is completely unbalanced. The generator is still producing positive sequence voltages and currents, but at the fault, the positive sequence voltages fall to 2/3 of their pre-fault values. So once again, let's see how the positive sequence quantities are transposed into the unbalanced voltages and currents at the fault. Now remember our previous conclusion. Any unbalanced fault has negative sequence components acting on the positive sequence quantities. Now where a ground fault is present, we need to add yet another set of components. First, let's look at the voltages on line A. At the fault, VA equals 0. VA1 has been canceled out by the negative sequence voltage VA2 and the missing component, which we call VA0. Now that we have placed VA2, we can draw in the other two negative sequence voltages, that is VB2 and VC2. We know that these components are 120 degrees apart. They are equal in magnitude and rotate with the phase sequence ACB. Now let's look at the B phase components. We know that this phase voltage, VB, remains unchanged. Thus, the fault voltage, VB, is the sum of VB1, VB2, and the missing component, VB0. Check in your workbook to verify that these phasors add to give VB. Similarly, with the C phase voltages. The phase voltage VC at the fault is obtained by adding VC1, VC2, and the missing component VC0. Now, another interesting factor becomes apparent. The V0 components in each of the phases are of identical magnitude and all are at the same phase angle. In fact, these voltage components have no sequence at all. So they are called zero sequence components. To review, to get each phase voltage at the fault, we add the three components together. For example, VA equals VA1 plus VA2 plus VA0. Now let's look at the currents. First, it is apparent that the current at the fault, IA, is about 3 times the magnitude of the positive sequence, IA1. The difference, of course, is made up by the presence of 2 other sequence currents, IA2 and IA0, which are of the same magnitude and in the same direction. Thus, these phasors, IA1, IA2, and IA0, add up to give IA. Now that we have located IA2, we can draw in the other 2 negative sequence components, IB2 and IC2. We can also now add in the zero sequence current components, remembering the characteristic that they are always in the same angular direction. We know that the current IB is 0, and this must equal IB1 plus IB2 plus IB0. That is, the positive and negative sequence phasors IB1 and IB2 cancel out the zero sequence phasor IB0, and thus the total is 0. Similarly with line C, IC1 plus IC2 plus IC0 equals 0. This is what we should expect. There is a heavy flow of current in the grounded line, but there is zero current flowing in the uninvolved phases. Remember that we are assuming load to be 0. Again, we have seen that the sum of the positive, negative, and zero sequence components for each phase add up to give us the actual fault values. So we now come to another very important conclusion, and that is where a ground fault exists, all 3 sets of symmetrical components are present. That is, positive sequence components, negative sequence components, and zero sequence components. And do note that within each set of components, the voltages and currents are of equal magnitude. The presence of these components provides a useful tool for detecting unbalanced conditions and ground faults. For protection, both zero sequence and negative sequence relays are installed. Typically, the negative sequence relay works by comparing voltage or current in all 3 phases and filtering out negative sequence components. The current coils are connected to CTs like this. The current flowing through each coil will be the sum of positive, negative, and zero sequence currents in that particular phase. Note that the zero sequence components, as they are all in phase, add together at this point and pass through the ground relay current coil. Now let's look at the VT connections. The primary and secondaries are Y-connected with grounded neutral. The secondary supplies potential containing positive, negative, and zero sequence components to the relay's negative sequence voltage coils. This enables the relay to detect the presence and magnitude of negative sequence voltages. Additionally, to detect zero sequence voltage, an auxiliary transformer can be connected like this. The primary is Y connected with the secondary in broken delta. The zero sequence voltage in each phase is summated and fed to the voltage coil of the ground relay. We'll be talking more about this in future tapes. The wide use of these relays serves to indicate a practical application of the study of symmetrical components, as well as their use as a mathematical tool in analyzing fault conditions. Our main objective at this point is to introduce the concept of symmetrical components and show how useful this method is in analyzing fault conditions.
When faults do occur, the power system no longer operates with beautiful sine waves and balanced phasors. At any instant in time, we may have voltages and currents going in several directions, with magnitudes and phase angles being imposed upon each other.
Breaking the quantities down into symmetrical components helps us visualize the conditions. In fact, any unbalanced system of currents and voltage can be represented by a combination of positive, negative, and zero sequence components.
There are several basic rules we should remember in connection with this method. Only phase voltage components are used. The load current is considered to be zero, so that only fault current flows. Current in the uninvolved phases is taken as zero. The study is simplified if the phase angle of the fault path impedance is taken as zero. Only positive sequence voltages and currents are created in the generator. Under perfectly balanced operating conditions, only positive sequence quantities are present throughout the system. Negative sequence and zero sequence quantities are considered to be generated at the fault.
With unbalanced conditions, negative sequence quantities exist as well as positive sequence.
Where a ground fault exists, all three types of symmetrical components are present. That is, positive sequence, negative sequence, and zero sequence. The zero sequence quantities have the same phase angle in every phase at any instant in time. Summation of the positive sequence, negative sequence, and zero sequence quantities will show voltage and current conditions at the fault. We have included in your workbook this chart, which shows the positive, negative, and zero sequence components of current and voltage for the most common fault conditions.
Please take your time to go carefully through each one of these items until you're satisfied that you understand the various combinations of positive, negative, and zero sequence components. Well, at this point, we all deserve a break and time to fix this material in our minds. So please switch off the tape and thoroughly review your workbooks.